welcome to our first class here in Renewable Energy Systems. Today we're gonna discuss some topics about efficiency and we're gonna solve some problems. Our problem will contain efficiency aspect, how it affects the cost price, where it's initial cost and running cost. We will go through some examples and we'll see how things will going to go through. Okay. So first of all, first the problem here we have, he asked me to compare the direct cost of to the consumer of using a succession of 100 watt incident light bulbs with an efficiency visible light of 5%. What does it mean to have efficiency of 5%? Which means that the amount of energy it takes from the energy source, only 5% of it is turned into illumination, and the other 95% is lost as heat energy. Okay. So we have a lifetime of 1000 hours and the price of each 50 cents. Okay, and we want to compare it with a one fluorescent lamp giving the same illumination at 22% efficiency with a lifetime 10,000 hours and the price of $3. Assume the price of electricity is 10 cents per kilowatt. Okay, great. So we wanted to compare between the consumption of each light source, whether it is an incandescent bulbs or it is a fluorescent lamp. So what I'm going to do right now is I'm going to calculate the cost of each one and compare. Okay, so let's start with this one, which is our incidence bulbs. So we have 10 bulbs, each one consumes 10 watts. Okay, but I'm gonna be costed upon 10 watts, not upon the 5% I'm getting it. So, and we have a lifetime of 1000 hours. Okay, so we have 10 bulbs, 100 watt for each lifetime 1000 hours. Let's calculate the energy. So, energy equals 10 bulbs, which is the number of bulbs, times 100 watt for each, so it's the total power for all bulbs, times the lifetime, which is 1000 hours, 1000 watt. So we have 1, 2, 3, 4, 5, 6. We have 10 power 6 kilowatts. No, it's 10 power 6. Okay, so now I have like 10 power 3 kilowatt hour. So that's our energy consumption for the bulbs. Okay, so let's calculate the cost. The initial cost, the price of each is 50 cents per each. Okay, so the initial cost equals to 10 bulbs times 50 cents. 50 cents equals to $0.50. Okay, so equal about $0.5. So we have 50. No, sorry. So we have $5. Okay, come on. Princess. So we do have $5 for initial cost for the 10 bulbs, and I want to calculate my running cost or my electricity consumption. So I'm gonna to call it like it's running cost equals to, I do consume a year 10.3 kilowatt hour, and I do have as a consumption for each kilowatt hour, which is 10 cents. So 10 cents is $0.1 per kilowatt hour. I'm gonna multiply our consumption 10.3, which will equal to $100. Okay, so my running cost will be $100, my initial cost will be $5. So my total cost for using incidence bulbs would be equal to 100 plus 5, which equals to $105. Okay, so that's for the incident bulbs. Okay, I calculated the initial cost, my running cost, and from the energy consumption, I calculated my running cost. Running cost is a term code for operations like more for maintenance stuff, but in our problem here, we are telling it it's a term like running cost, not for maintenance, but for its energy consumption among this period. So you're gonna understand the different meanings between both. So let's start calculate for our fluorescent lamp and see how things will go. Okay, great. So our fluorescent lamp, I do have a problem here. Right here, I do know how much energy does it consume. But here I don't know, sorry, power. But here I don't know. All I know, it gives the illumination as the incident bulbs, but it uses 22%. Okay, so I want to get the power. How could I get it? Okay, so power of the fluorescent equals to illumination energy over given energy. Okay. So not over the given energy. That's one I want to know over the efficiency of it. So if I do know my efficiency, which is 22%, over the efficiency. So the efficiency times the power given to the fluorescent lamps gives me my illumination energy. Okay, so I do know that the illumination energy or the power of illumination is the same as for the incident bulbs. So what I'm gonna do is gonna take this 100 watts and multiply it by this 5%. So it's gonna equal to 100 times 5% all over 22%. So the power required for each fluorescent lamp, or the power required, as I had only one, would equal to, I will calculate it, how much it will be equal to. Okay, wait a second. It would be equal to 22.72 watts. So you do see the difference. My fluorescent lamp uses 22.7 watts and our incident bulbs use 100 watts. Okay, so let's continue our costing process. So the price of each is $3 and I only have a one, so I would type my initial cost would equal to how much? $3. Okay, my running cost equals to my power times my lifetime times my consumption cost. Cost is cost like each, no. Okay. So it's equal to 22.72 times 10,000 hours, which is a longer lifetime as my incidence bulbs have a lifetime of 1,000 hours, times 0.1, which would be equal to 4 zeros times 0.1 would be 3 zeros. So my running cost would be $22.72. Is it right? How much would it be? 22.72. Okay, I didn't convert this to kilowatt as it's kilowatt hours, so I'm gonna divide this by 7. So 3 zeros will cancel 3 zeros, and I do have a mistake here. 22.72 watts, okay. And times 10,000, okay, times 0.1, okay. So this will be at 10,000 Yes. So it's going to be the same, like $22.72. Okay, I'm right. So my total cost would be equals to $3 plus 22.72 equals $25.72. Now all you do is compare between the total cost of my incident bulbs, which is $105, and my total cost of my fluorescent bulb, which is $25.72. So due to efficiency and long lifetime of fluorescent lamp, it's a good, better choice, even if its initial cost is way higher than the initial cost of my incident bulbs, as each one is 50 cents per each, but here my price is $3 per each. So if you're gonna make a choice, choose the fluorescent lamp. Let's go for another example. Okay, so our next example here is like a little bit more tricky. It tends more to be a mathematical question than it's an engineering question. So let's read it together. Okay, so he asked me to consider a nuclear power plant whose power level is ramped up from zero to an increase to maximum 7 megawatts and then back down to zero over a 10-hour period of time. Assumes that the power level varies as a quadratic function of time during those 10 hours. Write an expression for the power as a function of time. Then find the total energy generated by the plant during the 10-hour period. So he's not only requiring the total energy uh, during this period, he is also requiring for power function as a function of time. So my problem here depends on your way of understanding or remembering the quadratic function. Okay, what's a quadratic function? As a starting brief, you know, for a quadratic function, let's write it here. Quadratic function. For basic info, like I'm a regular student, I don't know, it's something like in this shape, right? Whether it's increasing, decreasing, increasing, or it's increasing, decreasing, but it's like a bell shape. And it does have the equation of y equal ax squared plus bx plus c. That's the equation of our quadratic function. So if I'm gonna put my information here on a quadratic function, which one would I choose? The decreasing increasing one or the increasing decreasing one? Well, he told me that my energy or my power ramps up from 0 to 1000, my energy from 0 to 1000 megawatts, and then decreases to 0. So I'm increasing, decreasing. So I would choose the second type. So let's draw it together, okay? So I'm not very good at drawing, but I'm gonna try to. Okay. Yes, it's beautiful. So this one and this one. Okay, so here our time. Time 0 hours, 10 hours, and as it's quadratic, so it's symmetrical. So my maximum point over here is at 5 hours, or this value is 1000 megawatts. Okay, I will use my equation and my information over here to get the power function. Then I will get the total energy. And before we will start, you don't know how to get the energy. So you have a function, you want to get the total energy. Energy is a summation of power times time. So it's the area under this curve, which is the energy. Okay, so let's solve that it out together. I'll use the purple one. My equation says y equals ax squared plus bx plus c. I do have a series of points right here for this function. I have a point 0, 0. Okay. I have a point 5 and 1000. And last and at least 10 and 0. Two informations, two unknowns, we're gonna solve this. Okay, so if I plug in y equals 0, x equals 0, it's gonna meet me like c would be 0. Okay, let's type the 5 and 1000. Y equals 1000 and x equals 5, so it's 25a plus 5b. Wait a second to fix the lighting. Okay, this is the first one. Our last one, 10 and 0. So we have a 0 equals to 100a plus 10b. And that's equation number 2. Okay, let's solve 1 and 2 together. But I'm not going to do it with substitution. I'm going to use omitting method. So I'm going to take equation 1, which is 1000 equals to 25a plus 5b. I'm going to take equation 2 and divide it by 2 and plug it down here, down 1. So 0 divided by 2 equals 2. 100a divided by 2 equals 50a. And 10 times divided by 2 equals 5b. Okay, and I will subtract them from each other. Okay, so I would here have 1000. Here I would have negative 25a. And here I would have a 0. So my a would be 4 times 25, 100. So it would be negative 40. Negative 40. And if I did plug in a in any equation, so negative 40 times 100, negative 4000. Other side gonna be 4000 divided by 10, so b gonna be 400. So my equation will be y equals 400x squared, right? Or no, a equal negative 40. Negative 40 x squared plus 400x. Okay, so my equation y equal negative 40 x squared plus 400x. Right now, I'm gonna take this equation and integrate it from 0 till 10 to find out our area. So, area for energy equal to 0 and 0 to 10. Our function here, negative 40 x squared plus 400 x dx. Okay, simple integration, simple one. So I'm gonna add 1 to the power and divide it by a new one. I'm gonna add 1 to the power divided by a new one. So 400 divided by 2 equals 200 x squared. My integration boundaries are from 10 to 0. I'm not gonna substitute by 0 as it will gonna leave me, this equation will be 0, so I'm gonna put the 10 and energy will be negative 40 10 power 3 divided by 3 plus 200 multiplied by 100, and all of this will be equal to how much? 6,666.6 megawatt hour. Why it's in a megawatt hour? Because the measuring unit of power here is megawatt and the time here is in hours, and that's our next question. So it all rely on your information about quadratic function. You have to know its format and which one you would choose depending on your problem. You are saying you are increasing and then decreasing. If it stayed the opposite way, it's started by a given power and decreased to zero and then raised again. So we would use this one, and that's all. Okay, let's go for the next one. So our third problem here is an easy one. Doesn't have any tricks. It's like a bit more on the conversion side. So I have written here the given and I have written here the conversions we are going to make. So let's solve it together. Okay. The problem says the United States generates and uses about 71 quads of energy per year, and its renewable sources generate about 40 gigawatts. Okay. If the renewable sources are generating power about a third of the time, what fraction of its energy usage is based on renewable resources? Okay. So how gonna we solve it? Always saying that the United States uses 71 quads of energy per year, and the renewable energy sources generates 40 gigawatts, and it generates it like third of the time. So we are gonna calculate our problem on a year. So let's write it down. 1 year, like it have how many hours for third year? A year have 365 days, 24 hours to each day, and renewable energy sources generates third of its time. So the time for renewable resources we're gonna cut it down to RR, renewable resources, equals to 365 times 24 over 3. This would be equal to 2920 hours. 2920 hours. Okay, that's it. So I do have my power for my renewable resources. I'm gonna convert it to energy over this period of time. So energy from RR, renewable resources, equals to 2920 times 40 gigawatts. This would be equal to, okay, let's write fast. As my brother took my calculator. So we're gonna use 2920 times 40 equals to 116800, which is gigawatt hours. Okay, great. So right now what I'm going to do is I'm gonna convert my gigawatt hours to quads, as he's telling me or giving me this measuring unit in quads. So you have two ways. The first one, you can get this 71 and convert it to gigawatt hour, like from this equation. And the second way is to take this number and convert it to quads. So I'm gonna take this number and convert it to quads and divide it by this number. So we're gonna know the fraction of renewable energy participating in the energy of the United States. So energy from renewable resources equals to, I'm gonna convert it first to kilowatt hour, then multiplied by this number and divided by 10 power 5. Okay, so I'm gonna take this number 116800. I'm gonna to take it from giga to kilo. What giga is 10 power 9, kilo is 10 power 3, so the difference between them like is 10 power 6. Okay, great. So I'm gonna multiply it by 10 power 6. Then I'm gonna multiply it by this number times 3412. Convert it to BTU. Then I'm gonna convert it to quads. So each quad contains 10 power 15 BTU. So I'm gonna divide it by 10 power 15. This will be equals to, let's use our calculator, 116800 times 10 power 6 times 3412 over 10 power 15. This would be equal to 0.398 quads PTU. Okay, so the fraction of participation for renewable resources fraction, this will be equals to this number 0.398 divided by our 71 quads. It's like a two little number. How much would it be? 0.398 divided by 71 is gonna equal to 0.5%. Like after you multiply by 100, it would be 0.5%. So the participation of the renewable energy resource in the United States fraction of energy is like 0.5%, like a two little number. Okay, great. Let's go for our last example. Okay, let's go for our last problem. Our last problem here says, how large would a square side L be? Okay, how large would a square side L needed to be if we recover 10% efficient solar cells? So our given we do have solar cells efficiency 10%. Okay. In the Sahara Desert, the power generated would be enough to satisfy the world's present energy needs. Okay, so we have the world's energy needs. Okay. Assume that the incident solar radiation striking each square meter is approximately 1000 watts. So energy striking equals to 1000 watts per meter square. This energy is coming from, or this power is coming from our lovely sun. Okay, great. So I'm gonna use what's required. Okay, it's required. So we do have a land like this. It's in a square shape, so that's L, and that's L, and this area equals to L squared. All it's required, I want to determine the area, or I want to determine the side length. So if I got the area, I got the side length, which would generate electricity with solar cells for the world's energy needs. So first of all, I do have to understand or to know what's our energy demand. So our world's energy demand is like 71 watts. It's like information, I Google it, and if I gonna give you an example like this, I will give you the world's energy demand. So the world's energy demand is 71 watts. Okay, just wait a second. I will refill it. Okay, it's refilled now. So it's 71 watts. So all I'm gonna need to do is convert this 71 watts into watts with taking consideration this efficiency and now the side length. Okay, great. So let's convert 71 watts into how much? Okay, I'm gonna multiply it. 71 watts BTU kilowatt hour. We'll need to multiply it like number of hours. Okay, to convert it into watts. Okay, great. Oh, divided by the number of hours. Okay, good. So, world's demand equals to 71. Okay, multiplied by 10 power 15. So it's BTUs divided by 3412. So it's kilowatts, and divided by number of hours. So it's 365 multiplied 24. That's the world's demand in hours. No, watts is joule per second. So I'm gonna convert it into times 60 times 60. Okay, is this calculation right? Yes, that's right. So from this equation, I'm gonna get how much? 2.375 times 10 power 12 watt. 2.375 times 10 power 12 watts. Okay, just wait a second. I'm gonna check if my phone is still recording or not. Okay. So we are still recording. Okay. So that's the word demand for watts. Okay. So that's the word's demand from watts, like joules per second. Okay, so I wanted to consider this area. So I do know that the sun gives out 1000 watts per meter square, and my efficiency is 10%. So 10% only from this 1000 is instant to my area. So incident power absorbed by my solar cells equals to 1000 times 10%, which is equal to 100 watts only. Okay. Right now I want to calculate my area. So each meter square gives out 100 watts. How much area does it require to give this number? So we're gonna use 100 watts times area equals to this number, 2.375 times 10 power 12, give us our area to be 2.375 times 10 power 10, and my area, as it's a square shape, is equal to L square. So the side length would be root this number, 2.375 times 10 power 10, which is equal to 154 kilometers. So I will need a square with a side length of 154 kilometers to give the world's energy demand from solar cells of efficiency 10% and the sun emission or radiation or energy output from sun 1000 watts per meter square. And that's all. Thank you for watching and wait for us for the next video. Bye bye.